Hello everyone, my name is Nicolas Rodriguez. Today I will take about the article Kate as word machine and electromagnetic induction, a real quantitative experiment analysis students. Electromagnetic induction, or EMI, is a process where a sharing magnitude 5 generates an electric current. This phenomenon is central to understanding many areas of physics, including technologies like electric motors, transformers, and wireless sharing. However, EMI can be a difficult concept for students to grasp, as it requires an understanding of both managing fields and how they change over time. The article Ashworth machine and electromagnetic induction, a real quantitative experiment to analyze students' ways of reasoning, explorers, and approaches to teaching EMI that uses a special device called an electromagnetic Ashworth machine. This setup allows students to observe EMI in action, do hands-on experiment and see real-time data, helping them connect theory with what they are seeing and museum. The study involved high school students working through three main sets: understanding magnetic fields. In the first step, students explored magnetic fields using a compass. They observed the compass nearest behavior around magnets, which helped them understand the concept of magnetic field lines and their symmetry by drawing out these field lines. Students could visualize how the magnetic field is structured around magnets. This was a foundation activity as understanding magnetic fields is necessary before device into EMI. Exploring electromagnetic induction, EMI. Next student experiments with creating an electric current in a coil of wire without using a battery. They found that moving a magnetic in and out of the could induce a current, shown by the movement of a galvanometer connect of the coil. This hands-on experiment helped us see that EMI doesn't depend solely on the movement of the magnets inside. It's more about change in the magnetic field around the coil. This site also introduces students to the idea that EMI can happen in various ways, not used by moving a magnetic through a coil. Quantitative experiments with the Atwood machine. In the final stage, students use the Atwood machine to conduct real-time quantitative experiments. The machine consists of a magnet suspended over a coil, allowing students to track the magnet's movement as it falls down the coil. Sensors connected to the machine measure the current generated as the magnet moves, and a student can see graphs of this change on a screen. This setup helped a student visualize how the change speed or positive of the magnetic effects. The induced current student observed that as the magnet accelerates down the coil, it produces two distinct peaks in the graph, one as it enters and another as it exits the coil. This pattern revealed that the changing rate of the magnetic field, not use its presence, is key to generate an electric current. This process is explained by the Faraday-Neumann-Lenz law. If Nickel showed students the role of time in M. Though the steps students gradually moved from simple observations to more complex ideas. At first, many students believed that only the motion of the magnet caused M. But though these experiments, they learning that M is actually caused by the variation in the magnitude field over time. Seeking this play out in real time growth allowed them to understand the Faraday-Neumann-Lenz law more constantly, which states that a change magnitude field in coil will induce an electric current with a direction that opposes the change. The students' results show that the hands-on learning combined with real-time data visualization can make changing physics concepts like electromagnetic induction more accessible and understand students were able to connect the abstract theory of EMI with the physics process happening before their age. This approach could be valuable in teaching other difficult topics in physics by making the sciences interactive and relative. It suggests that combining direct observation with theory can help students move past common misconceptions and void a more accurate understanding of complex phenomena.